Welcome, everyone. If we get settled for the last speaker session of the day, this is plenary session 4. I'm Tiku Majumder from Williams College, and I'm chairing the session. There'll be 2 talks. This is the first of 3 precision measurement sessions. The first talk will be given by Ekkehard Peik, atomic and nuclear clock for testing fundamental physics. Please.
Much. Yeah, good afternoon. It's a great pleasure for me to be here and to present our work. I would like to thank the organizers for putting this together and for inviting me. So I will, oops, this was not what I meant. I will speak about atomic and nuclear clocks for testing fundamental physics. Work is performed in the time and frequency department of PTB, which is Germany's National Metrology Institute in Braunschweig. So the experimental toolkit that we are using is shown here. So it is doing laser spectroscopy with single trapped and laser cooled ions in a Paul trap. So we are using the Paul trap to to store single ions. This provides the long interaction and coherence times for long interrogations. The trapping is combined with laser cooling, so this localizing the ion in the lamp Dicke regime that is on a length scale well below the optical wavelengths that we are measuring. We are detecting the ions via the fluorescent. They emit on this cooling transition, so you see a nice picture of a single ion. And this combination of trapping and lamp Dicke confinement eliminates or reduces much of the systematic frequency shifts, most notably the Doppler effect, the Doppler shifts, the motional shifts in spectroscopy. So the technique is well suited for obtaining very high resolution spectroscopy in forbidden transitions, and because of the good isolation of the ion from external perturbations, one has excellent control of systematic shifts and can obtain Hertz level or sub-Hertz level spectroscopy. In order to use this for measurements or for a clock, of course, the stability is another important criterion, and this is of course limited by the fact that we are doing the experiments with just a single atom or a single ion, so we are limited by the quantum projection noise in the state detection. It means that since typically we have an optical resolution like 10 to the 15, we get like for 1 second interrogation, we start with an instability of about 10 minus 15 in 1 second, and then it averages down like 1 over square root tau. It means that going to the 10 to the minus 18 regime, where actually the uncertainties of our clocks presently are, requires like 10 days of averaging. And the motivation for this work, it is of course, I mentioned work done at the National Metrology Institute. So one primary motivation is to look for the next generation of atomic clocks that will one day maybe replace the cesium clocks for the definition of the SI second. There will be a new redefinition of the SI second maybe in 10 years' time after further developments and discussions. But today actually I'm going to speak predominantly on the uses of the very high precision and accuracy in these clocks for clock-based searches for new physics, so searching for violations of fundamental principles. This is an overview of the laboratory. It's quite a remarkable place, a big 250 square meter laboratory room designed for housing the ensemble of primary clocks designed in the 1960s, when people would have quite different ideas of how this ensemble of primary clocks would look like than we have today. But so you see here the 2 primary cesium fountain clocks of Germany that are responsible for legal time in Germany and for realizing the SI second. But you see that actually much of the space is taken up by the ytterbium plus ion clocks. 4 generations of them, different developments of the physics packages. We continue to run the older experiments. We put them partly now into continuous operation. We also have here one clock developed with the aim of having an autonomous and maybe even commercially available system developed together with industry and also based on this ytterbium ion. So the outline of my talk, I will briefly introduce these significant features and some properties of the ytterbium plus ion for the clock, and I will mainly speak about uses of these clocks for searches of new physics, like variations of time dependence of fundamental constants. And a little bit as an outlook, I will speak about the further reaching development of a nuclear optical clock with thorium, where we have done preparatory VUV laser spectroscopy of trapped thorium ions. So this is about ytterbium plus. I'd like to introduce a little bit why it is has so nice features for clocks and also for quantum information processing. So the level scheme, sorry, I will learn to see. The level scheme is shown simplified here. It's basically a single electron system. So there is an S1/2 ground state. There is a strong dipole line to a P level that is used for the laser cooling and the fluorescence detection. And then as a reference for the clocks, we have two forbidden optical transitions originating from the ground state and then going to excited states of higher angular momentum that happen to lie below the P states, and that's why these states are metastable. So there's a D level that can decay to the ground state only via the emission of electric quadrupole transition. It has about 3 Hertz natural line width, and then there is an even lower state with a higher angular momentum, an F state, so differing by 3 h-bar in angular momentum from the ground state, so it can only be excited or decay by the emission of electric octupole radiation. It has a line width of 3 nanohertz, and it has very favorable properties for the clock, so we have been able here to control the systematic uncertainty in the low 10 to the minus 18 range. And so we have an opportunity to compare to different transitions in the same atom. And also this is what makes the system interesting for the fundamental tests. And this can be understood by looking at the electron configuration. So in the ground state, we have a single 6s electron outside the closed 4f shell. And the excitation of the quadrupole line is really the promotion of the 6s to the 5d state. So we have a higher valence electron. But the octupole transition is quite different. So it opens the closed 4f shell. It creates a hole in the 4f shell, promoting this 4f electron to the 6s shell, filling the 6s shell. So the spectroscopically relevant feature here is a hole in the 4f shell, somewhat shielded or surrounded by the spherically symmetric 6s shell. And this is what makes this state relatively inert against external perturbations. And also, since the spectroscopic properties of these 5d electron and the 4f hole are very different, it makes the system sensitive to tests, for example, of relativistic effects, because this can be expressed or quantified by giving the sensitivity for the transition frequency to the value of the fine structure constant. So imagining possible changes of the fine structure constant, the relative change, the relative impact of such a change on the transition frequency for the quadrupole would be like a sensitivity of 1. And for the octupole, it would be -6. So quite different change of sign and also a different sensitivity. The transition here for the octupole transition is actually the highest one that is for the present high precision available optical clocks. This is a result of ab initio calculations, atomic structure calculations. So next step, I would like to speak a little bit more about this octupole. I've written down here 3 nanohertz natural line width. How do we know? We decided it's quite an important parameter for the clock, and so we should measure it. It was known only with significant uncertainty, because such a long lifetime here of this state is actually, it's a problem. It's difficult to calculate. The red dots here indicate a number of ab initio atomic structure calculations, and these are very difficult for this problem because of this opening of the 4f shell. So there's configuration interactions, and very many electrons have to be taken into account in ab initio to calculate this. And it's of course also very difficult to measure because, well, nobody will wait for for 1 year for this excited level to decay. So the measurements were actually based on excitation strengths. The blue dots here were done at the British NPL, and they had quite an uncertainty spanning over several years. Of course, in the real experiment, there will not be radiative decay, but the F-state population will be quenched either by collisions or by some non-resonant laser excitation. So the way we tried to measure it was to use our clock and to rely on the coherent excitation of this octupole transition, and then we want to determine the matrix element. It is of course linked to the lifetime by Fermi's golden rule. And so instead of measuring the lifetime, we try to measure the matrix element. And the matrix element also enters of course, in the resonant Rabi frequency when we coherently drive this transition. So we can measure the Rabi frequency, which is basically the product of the matrix element and the laser field strength that we use to drive the transition. Now the laser in this case of the strongly forbidden transition, it does not only do the coherent driving, but because the transition is strongly forbidden, there is also the same laser also does non-resonant dipole coupling to other levels in the atom, and so it produces a quadratic Stark shift or light shift, which is proportional to the laser intensity, so to the square of the laser field strength, and then to the differential polarizability at the laser frequency. So now we are doing the experiment with a single ion, and you see both quantities that we can measure precisely, the Rabi frequency and the light shift. They both depend on the laser field strength, and so we checked that the square of the Rabi frequency should be proportional to the light shift. So we did the experiment measuring Rabi oscillations for different laser intensities, and then checking the linearity between the squared Rabi frequency and the light shift. And from this we get an experimental result for this frequency ratio, which is now independent from the laser intensity, and which contains a matrix element, and in addition also the differential polarizability. And in order to measure this differential polarizability, it's hard to measure the field strength, but one can measure the integral power or the integral power of the laser. So we did this and then combined this with light shift measurements while scanning the laser over the position of the ion at multiple positions. So we obtained this number, and putting things together, we obtained, like with a 5% uncertainty, the matrix element or the radiative lifetime, which turns out to be about 50 million seconds or 1.6 years, a little bit at the lower end of these previous experimental investigations. So we know this number quite precisely now. So we are using the clock and the combination of the clocks for searches of new physics, and I will mainly speak about 3 different searches that we have performed. There is searches for violations of local position invariance. That is the question whether the clock comparison will depend possibly on time or space when it is performed. Specifically, we have been looking at temporal variations of the fine structure constant. We also looked already a few years ago at violations of symmetry of local Lorentz invariance by making use of the strongly anhomogeneous momentum distribution in the F state. And we also looked at coupling to dark matter, to ultra low mass scalar boson dark matter fields. I will briefly cover this today, and otherwise I also recommend you, for more details on these topics, to go to a poster presented by Melina Filzinger on Wednesday. So in 2017 already, we made an extended comparison of the octupole clock. So we had the first and second generation of our ion traps, storing a single ion each. using one common frequency stable laser with different modulators, and then exciting the two ions so that we could precisely measure the frequency difference between the two realizations of the octupole transition. And we did this for an extended period of time because actually we wanted here to look for Lorentz variation for daily and also yearly variations. But in terms of the frequency difference, the overall result here was quite satisfying. So we found agreement of these two clocks to within the low 10 to the minus 18 on the millihertz scale. So this is the overall result. We find within a combined uncertainty of 4 times 10 to the minus 18 an agreement of the two clocks. This is how the instability averaged down into the 10 to the minus 18 range after several days or weeks of measurement. We exploited this actually for as a search for Lorentz invariance, but now recently we have more focused on comparisons of the two different transitions because of the different sensitivity to the value of the fine structure constant. So we did repeated measurements. A plot is shown here, showing data covering like 5-6 years of precision measurements. So we could do several things. We could operate one of the clocks on one transition, the other on the other. We could swap the functions. So in really to exclude relations or unseen systematic effects related to the different traps, and we could also use one trap, one ion, alternatingly interrogating the two transitions. So basically, to use one system as two clocks in an alternating way. And all these data were consistent and agreed well for this analysis here. So we measured the frequency ratio of these two transitions with an overall uncertainty of about 310 minus 17. This is limited by the systematic uncertainty of the quadrupole transition, which is somewhat bigger than for the octupole. And overall, the data set is nicely consistent. Now we use this data set for a test of violations of local position invariance, asking here specifically, is there a time dependence of these measurements? So we fitted the data here to a simple linear slope in time. You see there is a non-zero slope here, but it is not really statistically significant. It is all within the one sigma uncertainty range. And now we can relate this to the question, is there a time dependence of the fine structure constant? I mentioned already that the two optical transitions have different sensitivities, sensitivity factors to the value of the fine structure constant. So it's +1 and -6 for the two transitions. It means that the frequency ratio would react to a hypothetical change of the fine structure constant with an enhancement by a factor of 7. So the effect on the frequency ratio would be 7 times enhanced relative to the change of the fine structure constant. And so the overall analysis now in terms of the drift of the fine structure constant restrains the temporal derivatives, the relative temporal derivative of the fine structure constant to this value, which is consistent with 0. It's basically 1 plus minus 1, 10 to the minus 18 per year. And so, just to put it a little bit into perspective, this is a small number. Even if you think on a cosmological time scale, so you know the age of the universe is roughly 10 to the 10 years. So something 10 to the minus 18 per year is really a very small gradient. So this has improved, and so this shows the historical improvement in the uncertainty in this value of the gradient of the fine structure constant from with precision optical clock experiments for a long time. The most relevant data came from the mercury-aluminum ion comparison done at NIST. And here we could now in an independent analysis improve it by more than a factor of 20. And we have been, this result was published here early in 2021. And now recently we have been continuing to take more data. We have basically taken the first generation clock now into continuous operation for this test, and we have obtained more data, and you can see that the present analysis we have gained another about factor 3 in uncertainty here on this this value. And now this data set we have also analyzed in other fashions, not only looking for the linear drift, but one may of course ask, are there other time dependencies? Are there maybe oscillatory time dependencies? So for the Lorentz test, we looked already at daily and yearly variations, and here we have now from this nearly continuous data set covering more than a year, we have done a Lomsgagel analysis for a range of, for basically all frequencies, starting from the low millihertz range going into the sub-microhertz range. And now we are sampling very, very many frequencies here. So you see a range of fit amplitudes. There is the lower numbers, but relevant, of course, are the higher numbers. And you can see that they are basically flat over these several orders of frequency. The small increase here is still an effect of our servo system, which has a time constant of a few 10 seconds. But we can say that over this extended frequency range, basically this periodogram is flat, so there is no indications of significant deviations from wide frequency noise over this range. And this is relevant because it can be used in a search for ultralight bosonic dark matter, as has been proposed in this work by Avanitaka et al. Some time ago. So the idea here is that dark matter may be constituted by a field of an ultralight boson that behaves like a classical field and that induces oscillations at the Compton frequency determined by the small mass of this boson. And if hypothetically this boson would couple to electromagnetism, it would lead to oscillations in the fine structure constant at the Compton frequency of this particle, and these oscillations would of course appear as oscillations in the frequency ratio. And we have done this analysis, and you can see here for comparison we have plotted in this graph together now over the mass of this particle. You can see it's really ultralight masses. It's 10 to the minus 16 to 22 electron volts. And we have, with the high availability of the clock and the high sensitivity, we have been able to improve on other recent clock tests of looking for this scenario. An additional aspect that we have looked on for the octupole transition, it's quite an special kind of forbidden transition. We have tried to excite it in a way that can reduce this effect of the light shift. So the small matrix element, of course, leads to a strong non-resonant coupling of the light shift, and we have tried to excite the ion not with a plane wave, but in the center of a Laguerre-Gaussian beam. So this shows the picture of a Laguerre-Gaussian mode of second order. It can be produced with wave plates from the laser beam, and then we have focused this on the ion, have scanned the ion within this beam profile, and now have made the experiment to test if actually we can excite the ion in the dark center of the beam. And the idea would of course be that the octupole transition could still be driven by the curvature of the electric fields that we have in the dark center, but if the center would be perfectly dark, there would be no electric dipole coupling, or the dipole coupling would be strongly reduced, so we should be able to excite the transition with reduced light shift. And indeed, this is what we observed. So we have again measured, we have placed the ion in the vortex, measured the Rabi oscillations, and then so from the Rabi oscillation we know the interaction strength. Then we have taken a spectrum. The spectrum gives us a light shift, and we have observed like a 5-fold reduction of the light shift relative to the case of focusing with a Gaussian beam fundamental mode. An experiment like this has been done previously in Ferdinand Schmidt-Kahler's group on the quadrupole transition, but we were the first here to do it on the octupole transition. Now, a factor of 5 reduction is not so spectacular. It is limited by the fact that the dark center is not perfectly dark. There is still some stray light, some scattered light from the faceplates, and also the ion is not perfectly localized, but it's still moving, and this is what limits the factor. Okay, I would like to very briefly change gears to go to the nuclear transition, to the nuclear clock, which is in very instances very similar to what I have explained about the optical clock with the trapped ytterbium ion, but now that we are replacing the electronic transition in the atom by a nuclear transition. inside the nucleus with the ideas or promises to obtain much higher accuracy because some of the systematic shifts are not relevant inside the nucleus, a high stability because we can work with a large particle number, and also a sensitivity to new physics, also in the strong interaction, and also with a specifically high sensitivity to some effects. The system that we are working on is in a very low energy nuclear transition. It is in thorium-229, which has the lowest known gamma ray transition at about 150 nanometer vacuum ultraviolet. It's a magnetic dipole transition. Radiative lifetime is about 5,000 seconds. So in fact, you see it is much less forbidden than the electric octupole. But of course, it has very different and interesting properties in comparison to the electronic transition. And we have it is a subject that is studied in a number of groups for some time. There is still the big challenge of driving this transition with a laser, and we are now doing preparatory experiments to this. So we have set up a laser system to produce this tunable 150 nanometer radiation. So we are relying on 4-wave mixing in xenon gas. Xenon happens to have a 2-photon resonance at about 125 nanometers. So we are driving this with 2 photons at 250 nanometers, and then we are mixing it with a tunable infrared photon, and this produces then in stimulated 4-wave mixing, the tunable VUV photon that we want to use for spectroscopy. This is a nonlinear process. It happens in a xenon cell, but it needs high intensity. So we start with 2 CW lasers for the frequency control, but then we have to run them through pulsed amplifiers in order to obtain the intensity, do third harmonic generation to produce the 250 nanometers, produce a VUV in the xenon cell, and then we have to work under vacuum. So we have a vacuum beamline to connect this to the trapped ions. And now recently we have done first steps. Now this is not nuclear spectroscopy. This is electronic spectroscopy of a transition at 150 nanometer of this laser system, driving in thorium plus ions, driving a 2-photon photoionization, producing thorium-2 plus, which we can then detect via the fluorescence very nicely and free from background from these laser systems. So I'm showing you this to show you that we are prepared, and later this year we hope to use the system actually to perform first the search runs for the nuclear excitation on these trapped thorium ions. So with this, I'd like to briefly summarize. So I've spoken about optical clocks with ytterbium plus and the fundamental tests that we have been doing with them because of the nice combination of high accuracy and good availability that we have in these ions. So we have improved on a number of limits for violations. We have not detected new physics, but we have improved the clocks, and we have improved the limits on a number of these parameters. So in closing, I'd like to thank my co-workers in the 2 teams on the optical clocks with trapped ions and nuclear laser spectroscopy at PTB, and we also have very efficient external theory support for this work and are funded by several national and European funding agencies. Thank you very much for your attention.
Okay, we're open for questions, and we'll try the same approach of getting if we can, getting a microphone to you. Let's start right over here.
Amazing work. I have a question that connects the 2 parts of your talk. In the first part, you measured the lifetime of the state via the ratio of light shift and Rabi frequency. And then in the later part, you showed that if you have a beam with like a Gaussian mode, you can actually change that ratio. So I wonder if you have an unintended admixture, say from windows or other objects in your path, would that limit the precision with which you can determine the lifetime? Because that would change presumably the ratio between light shift and Rabi frequency?
So frankly, I think at the time we did not think about this effect, but I think our analysis has been pretty immune against this, because it would enter into the differential polarizability that we were measuring with the laser parameters that we have used for the excitation. And for this experiment, we were really scanning the laser over the ion and then integrating the light shift and integrating the laser power. And so with this, I think we have really measured the differential polarizability in a way that is independent of the precise shape of the laser beam.
So if you did this with a Laguerre-Gaussian mode, you would get exactly the same result?
Well, the Laguerre-Gaussian mode, of course, has slightly different selection rules with polarization, and so this is different. So, but of course, this was all done. The first part, everything was done with the fundamental Gaussian mode. I've not thought about all the details of how it would look with the Laguerre-Gaussian. It would be definitely much more complicated in the analysis. So that's only what I would like to say.
Thank you. Yeah, and then next. Yeah.
So my question is about the Laguerre-Gaussian beam and particularly about the selection rules. Now, the last time I looked, which was some time ago, there was a lot of controversy over whether the orbital angular momentum of light could be used to excite the angular momentum of atoms as opposed to the spin angular momentum of light. And there seem to be equally confident predictions on both sides of that question. Some people saying that there's no way that orbital angular momentum can have anything to do with the angular momentum of atoms, and other people who are saying, well, of course it does. And what I'm wondering is whether your experiments have helped to resolve this issue, or for that matter, whether you know anything more modern than I know about what the thinking is on this subject.
Mm-hmm. So for our case, I would say that definitely both effects can happen. Both effects can play a role. So the orbital angular momentum can be transferred both to the internal spin and also to the mechanical motion of the ion. In the experiment, we checked different polarization configurations, and I think we were also not in the quantum ground state, so we did not have perfect control of the orbital angular momentum of the atom. But our theory colleagues here, the group of Andrei Zuzhikov, has recently looked at this problem theoretically in more detail, and they find that exactly one can split the angular momentum of the photon, depending, of course, on the Zeeman sublevels or so. One can find situations where the angular momentum is split between the internal and the external angular momentum of the ion.
Did you try different charge states for the angular momentum, the orbital angular momentum of the light? That is, I assume that the data was an LG1, but you could have.
We tried both. We tried LGO1, LGO2,
yeah,
and also different polarization configurations.
And it worked the way it was supposed to, or? Could you tell?
It was. It is. The paper is just in preparation. So there is. We found qualitative agreement with the theory. There is quantitatively some scaling factors differences between theory and the experiments that we could not completely understand. One problem of the experiment was the localization of the ion. So we were maybe in the tense vibrational state,
yeah,
and we noticed also it was critical to focus the beam very, very tightly to like 2 microns or so, and so we were quite sensitive with optics outside the vacuum, so we were quite sensitive to vibrations and so on.
Yeah.
These were the experimental problems that may have made it difficult to really quantitatively analyze it.
Yeah, thanks.
Last question here.
Yeah, so really great work. I was just wondering about the laser line width of your spectroscopy laser. When you're trying to infer the radiative lifetime from your measurements like that, does the the line width of your excitation laser, how does that come into it, and do you know exactly what it is?
So what for basically we were just measuring Rabi oscillations, and so you saw maybe on the curves there was some damping of the Rabi oscillations visible, but which we are quite sure is not related to the laser, but is related to the motion of the ion. So our laser system, we are quite fortunate. It is referenced to the cryogenic silicon cavity at PTB, and so they have analyzed, the group of Uwe Ster, they have analyzed the laser to have line widths in the few 10 millihertz or so regime, and our laser is referenced to that. So the longest coherence times we have seen in the excitation of the ions was like in the range of 2 seconds, and it was limited by the motion of the ion and by the final last mirrors or so in front of the ion traps that were not interferometrically stabilized, but so the laser coherence time we believe was significantly longer in this experiment.
Thank you.
Okay, let's thank Ekkehard again for his talk.